When you hold a modern desktop processor, the smooth, metallic surface feels solid and continuous. But that exterior is simply a protective shell, sealing off an impossibly dense labyrinth built inside. A microchip is not a flat, two-dimensional drawing. This conceptual cross-section shows that a processor is a massive three-dimensional matrix, built vertically from the ground up. Looking at this structure, we can identify exactly 17 rigid layers of copper wiring. These are organized into three distinct tiers: global interconnects at the top, intermediate interconnects in the middle, and local interconnects at the bottom. And none of these wires are floating. They are firmly encased in solid blocks of insulating silicon dioxide to prevent short circuits. Those 17 layers of copper exist for one reason: to route electrical signals down to the foundational layer resting at the absolute bottom of the structure, the logic gates. This diagram outlines a single FinFET transistor as a base of the chip. The channels here measure exactly 36 by 6 by 52 nanometers, with a pitch of just 57 nanometers between each transistor. Designing an architecture at this scale requires precise physics, but the true engineering bottleneck is figuring out how to physically construct this layout in the real world without a single structural failure. To make this CPU functional, engineers must perfectly construct 26 billion transistors and weave a 17-layer copper maze above them without a single atomic-level alignment error. You cannot build a structure this complex upwards all at once, and you certainly cannot use mechanical assembly or physical tools to place the components. Instead, the entire architecture is built through a rigorous, repeating cycle of chemical and optical processes, adding a layer of material, patterning a shape into it, and removing the excess. To create a single processor, engineers run the wafer through this exact loop up to 940 times. The sheer volume of repetition means a single microchip takes 3 full months to complete. Truly understanding how our modern world is powered requires understanding the physical chemistry driving this relentless manufacturing loop. The cycle starts with a blank canvas, a flat, highly refined monocrystalline silicon wafer. In this cross-section, a uniform layer of blue insulating silicon dioxide is deposited across the bare silicon substrate. Next, liquid photoresist is spread evenly over the oxide, followed immediately by a soft bake to evaporate solvents and stabilize the layer. This photoresist is not a permanent structural component of the chip. It acts purely as a temporary chemical canvas, waiting to receive a blueprint. But having a chemically receptive canvas is useless unless engineers have a way to precisely draw billions of geometric shapes onto it simultaneously. That problem is solved by the photolithography tool, the mechanism responsible for transferring a digital design into physical reality. In this schematic, a top UV light shines through a physical photomask stencil containing the chip's layout. Internal lenses shrink the light pattern by a factor of 4. When this demagnified light strikes the wafer, it immediately weakens the exposed areas of the photoresist. This makes photolithography an incredibly efficient copy and paste mechanism, projecting complex blueprints across millions of nanoscale coordinates in a matter of seconds. Returning to the cross-section, the wafer enters the development phase. The UV-weakened photoresist is washed away to reveal exposed gaps. A hard bake then locks the remaining unexposed photoresist into a perfectly patterned nanoscopic stencil. With the stencil set, the loop moves to the subtraction phase. Here, plasma etchers are used to physically carve into the newly exposed gaps. High-energy plasmas carve vertically through the exposed blue silicon dioxide down to the previous layer. The temporary photoresist mask is then completely dissolved. Pivoting to the addition phase, physical vapor deposition floods these newly carved trenches with conductive copper until full. The wiring is now technically embedded in the insulation. But the deposition process inevitably leaves a sloppy, uneven overflow of copper across the top surface, which prevents the stacking of the next vertical layer. To solve this, the wafer must undergo a violent physical reset, known as chemical mechanical planarization, or CMP. As shown here, CMP applies chemical slurries and uses an abrasive pad to physically grind the top surface perfectly flat. What remains are isolated copper pathways sitting perfectly flush with the silicon dioxide. The completion of CMP marks the end of one cycle. Immediately, this exact loop begins again, using a different photomask layout for the next vertical layer. To build out the 17 distinct layers of wiring, a single CPU design requires 80 unique photomasks, and 80 passes through this exact loop. While building copper wires relies on adding and removing material, building the logic gates at the foundation requires an even more aggressive modification of the bare silicon itself. Engineers use ion implantation, hurling boron or phosphor atoms deep into the crystalline silicon lattice, which physically knocks the silicon atoms out of alignment. An annealer then applies intense heat, forcing the silicon to repair and realign, permanently trapping the foreign ions inside. Mastering the physics of these atomic-level manipulations is difficult enough in isolation. The true engineering test is scaling these delicate, nanometer-precise actions up to factory-level mass production. Stepping back from the nanometer scale, we enter the semiconductor fabrication plant. This is an ultra-sterile cleanroom facility spanning the area of 8 football fields, designed to execute the nanoscopic loop continuously. The base unit of production in this facility is the 300mm silicon wafer. This single disk acts as the structural canvas for a grid of 230 individual CPU chips. This schematic maps out the cleanroom floor. To execute the 940 process steps required for a finished wafer, the factory relies on an array of 435 specific tools, categorized into 6 distinct functions like masking, adding, and removing material. Because human breath or a single stray dust particle can ruin a nanoscopic pattern, wafers are moved in isolated stacks of 25, using sealed containers called front-opening universal pods, or FOUPs. To prevent contamination, FOUPs do not move across the floor. Automated overhead transport systems navigate the ceiling, delivering the sealed pods precisely to required tools. The tool receives the FOUP and mechanically lowers the wafers through vacuum load locks directly into the active process chambers. The silicon is never exposed to the ambient room. A modern fab is essentially a $170 million clockwork mechanism designed with one goal: protecting the microscopic perfection of the 940-step manufacturing loop. But despite billions of dollars spent on clean rooms and inspection metrology tools, manufacturing in the physical world is never flawless. When you are laying down 90 billion transistors across a wafer, microscopic dust particles and localized mask defects are statistically inevitable. Throwing away an entire 24-core chip because a single defect damaged one core is economically unviable, so engineers use a categorization system known as binning. This die matrix illustrates the process. If testing reveals a defective sector, that specific broken core is permanently disabled. The semi-functional chip is then down-categorized and sold to consumers as a lower-tier product, like an i7 instead of an i9. Once testing and binning are complete, the functional dies are extracted using a precise laser cut, permanently leaving the clean room behind. In the final assembly stage, the extracted die is flipped and mounted onto an interposer, which connects to a printed circuit board containing the physical grid that interfaces with the motherboard. Finally, it is capped with an integrated heat spreader to manage thermal output. The heavy metal block that sits inside your computer is the final packaged culmination of 3 months of the most rigorous chemical, optical, and logistical engineering ever achieved.